So we will start now. In the previous lectures of analog and digital electronics, we have started with the basics of operational amplifier, and the first kind of amplifier which we have seen is differential amplifier. Okay. So in the last session, we have seen the circuit configurations of differential amplifier, right? And we have seen the two different operating modes. One is known as differential mode and another one is common mode operation, right? The first one was differential mode of operation and second was common mode operation. So what was the basic difference between these two? See, when we talk about the differential mode of operation, at that time, the two inputs which we are providing to the amplifier, it will have same magnitude, but they will be 180-degree out of phase. Okay, so magnitude will be same, but the phase will be different. While in case of common mode of operation, what we are doing, we are having the same magnitude as well as same phase we are providing. Okay, and this is why the output voltage we are getting is 0 in this particular case. While in this case of differential mode, we will get output voltage double to the input voltage. Okay, so suppose our input voltage magnitude is 10 volt, then we will get output is equal to 20 volt. Then we have seen different circuit configurations. Right? So when we talk about these circuit configurations, we are available with total 4 kinds of circuit configurations. Right? The first one was over here. See, this is my two transistor biased circuits which are connected together. Okay, so this is the famous configuration which we have seen. It is to be supplied by plus VCC and minus VEE. These are my DC supply, and two input signals VS1 and VS2. This one is AC supply. Right now, whenever we are providing supply voltage to both the ends, at that time this kind of configuration is known as dual input configurations. And based on the output, how we are measuring the output. See, right now in these configurations, we are measuring the output between the collector of transistor 1 and collector of transistor 2. Okay, so this particular configurations can be called as balanced output configuration, right? So the first circuit configuration is known as dual input balanced output. Right? Now we have the second configuration. Okay, this is my first kind of configuration, and let us talk about the second configuration. So here you can see we are providing input at both the ends. Okay, at the base of the transistors Q1 and Q2. So definitely this is our dual input configurations. But now if you see output, okay, here you can see I am measuring the output between any one of the collector terminal with respect to ground. Okay, so this kind of configuration is known as unbalanced output. Okay, so the entire configuration will now be known as dual input unbalanced output configuration, right? Then coming back to next configurations, here you can see the output which I am measuring is between collectors of the both the transistors. So we are available with some balanced output here. But if you look at the input terminals, so I am providing some AC signal to the base of transistor Q1, but the base of transistor Q2 here is grounded. Okay, so I am providing only one input, and this is called single input and balanced output configuration. So we have third kind of configuration, which is single input but balanced output, right? And the fourth one is Again, single input is there because we are providing the input signal to base of the transistor Q1, but the signal is not provided to the base of the transistor Q2. And looking at the output voltage measurement, then we are measuring the output voltage in between the collector of transistor Q1 and the ground. Okay, so here we have unbalanced output. Okay, so this configuration is known as single input unbalanced output. Okay, so this is what we are getting, right? Now that is what we have seen, and we have seen the operation of this dual input balanced output configurations. Okay, we have also performed the DC analysis of this differential amplifier. Okay, and we know why we are performing the DC analysis: to obtain the operating point values. What are the operating point values? The value of current, that is ICQ, and the value of operating voltage, that is VCEQ. Okay, so we have done some mathematical operations on this circuit diagram. We have drawn the DC equivalent circuit. Now whenever I talk about the DC equivalent circuit, what does it mean? We will zero the AC signal sources, right? And only DC supplies will be considered. Okay, then we have applied some Kirchhoff's laws to get the desired values of this ICQ and VCEQ. Okay, so ICQ, or you can also call it ammeter current IE, and that was equal to VEE minus VBE divided by 2 times RE. Okay, this was the equation which we have derived. And talking about the operating voltage, then it is given by VCC plus VBE minus ICQ RC. Okay, so these two equations will give us the operating point of the differential amplifier, right? Here VB is nothing but the voltage between base and emitter. Okay, so in case of silicon it will be from 0.6 to 0.7, and for germanium it would be 0.3. Okay, depends on which semiconducting material we are using for manufacturing of the transistors, right? So this DC analysis and expressions for ICQ and VCQ will remain same for all the differential amplifier circuit configurations. Okay, though we have considered the case of this dual input balanced output amplifier and we are getting these two equations, but if you take dual input unbalanced output or single input balanced or unbalanced output, then also you will get the same equations. Okay, so there is no need to perform the mathematical operations on other three configurations because the result will be same, and we are getting the same equation of this ICQ and VCEQ. Okay, so now you know how you will be able to find out the operating point values of any configurations of differential amplifier. Okay, so for better understanding, let us start with some example. Okay, so I have one circuit. This is the circuit given to me, right? And we have to calculate the operating point values of this circuit, right? So now if you can see, plus VCC supply is having 12 volt, resistance RC is 4.7 kilowatt, RE is 3.3 kilo ohm, VE is 12 volt, and we have to measure the output voltage, right? So what is the values available to us is now collector resistance RC, which is equal to 4.7 kilo ohm, emitter resistance RE 3.3 kilo ohm, then VCC 12 volt and VEE is negative 12 volt. So we need to calculate the operating point values. What do you mean by operating point values? We have to find out the value of current ICQ and voltage VCEQ. Okay, so this will be our operating points. Okay, so now we are available with the equations of IE. You can see IE is given by VEE minus VBE divided by 2RE. Okay, so we will use the same equation. Okay, so IE is equal to VEE minus VBE divided by 2 times RE. Okay, now here you need to take care while selecting the value of VEE. See, basically when we talk about the VEE value, it is given to you negative 12 volt, right? But this negative value we have already considered while deriving the equations for RE. Okay, so you need not to take the value as minus 12, but initially you will only take the magnitude, that is 12. Okay, because negative value we already have considered in the while applying the Kirchhoff's voltage laws. Okay, so whatever value is there, that value need to be put. You need not to consider the sign, right? So in these equations now, we will have VEE is equal to 12 volt minus VBE. Okay, the voltage between base and emitter. Okay, over here, this is my voltage VBE. Now it is not given to you whether the transistors are made up of silicon material or germanium material. Okay, so whenever it is not given to you, data is not given to you, we need to consider that these transistors are made up of silicon materials only, because most of the transistors are manufactured using silicon material. Very rare applications are there where you will find the semiconductor devices which are made up of germanium, right? So we will consider VBE according to silicon, and that is equal to 0.7. Okay, divided by 2 times RE. RE is given to you 3.3 kilo. Okay, so upon solving, you will get the value of IE is equal to 1.712 milliampere. Okay, so this is the amount of ammeter current which is flowing through the circuit. And now we know, in the case of transformer, we know that IC is equal to IE, and that is equal to 1.72712 milliampere. So our first operating point ICQ is 1.712 milliampere. Okay. So this was the first point. Now we have the equation for finding out the VCEQ voltage also. Let us go back to equation. Here you can see VCEQ is equal to VCC plus VBE minus ICQ RC. Okay, so we will use the same equation to find out the voltage VCEQ. Okay, so voltage VCEQ is given by VCC plus VBE minus ICQ RC, and that is equal to VCC is given to you 12 volt plus VBE is 0.7 minus ICQ, just we have derived 1.712 milliampere, and collector resistance is 4.7 kilo ohm. So that will give us the value of VCEQ, which turns around 4.653 volt. Okay, so now we are available with the operating points of this differential amplifier. Okay, so we can say operating point or Q point is 1.712 milliampere and 4.653 volt. So this is how you will be able to solve any amplifier circuits. Okay, whether it is dual input balanced or unbalanced differential amplifier, or single input balanced or unbalanced amplifier. Okay, in all the four cases, the equation for ICQ and VCEQ remains same. Right? So this is about the DC analysis. Okay, whenever we have to find out the operating points, we will perform the DC analysis on the amplifier circuit, right? And for finding out other parameters, we are going to perform AC analysis. Okay, so in the AC analysis, we will calculate the differential gain, common mode gain, input resistance, as well as output resistance of the differential amplifier circuit. Okay, so now let us try to understand or carry out the AC analysis of differential amplifier. Okay, now there are two ways to carry out the AC analysis of differential amplifier. One is the using H parameters and another one is using R parameters. Okay, so we will analyze the circuit using H parameters, which are known as hybrid parameters, right? So you will get to know about these various parameters, hybrid parameters, Y parameters, etc. in circuit and networks subject. Okay, so we'll start with the AC analysis of differential amplifier. We have AC analysis of differential amplifier. Okay. So as I have told you that whenever we carry out the AC analysis, we will try to calculate the different gains. So we are available with two kinds of gain. One is the differential gain, another one is the common mode gain, right? So let us try to find out the first kind of gain, which is differential gain. It is denoted by AD. Okay. So for this differential gain calculation, now the two input signals must be different from each other. That is what we have seen. See, in this last session, we have discussed about the operation of differential amplifier, where we have talked about the two different operating modes. One is known as differential operation, then second one is common mode operating, right? So in differential operations, what we have seen is the two inputs are same in magnitude, but they differ in the phase. They are 180-degree out of phase by each other, and that will give us the differential gain. Okay, so these two input signals must be different from each other. Okay, so let us take the two AC input signals be equal in magnitude, but having 180-degree phase difference in between them. Okay, and the magnitude of this is HE input voltage be Vs1 and Vs2. Okay, so the ultimate difference will be equal to Vs by 2 between them. Okay, so I will have the circuit diagram first. Now here we are getting plus VCC supply, right? And this will be our transistor. This is my base of the transistor, where we have some source resistance Rs, and there will be AC signal, input signal over here. Okay, so we have considered this AC signal be Vs1, and Vs1 and Vs2 are same, so the magnitude will be Vs by 2. Okay, so let us say this magnitude Vs by 2. The source resistance Rs, sorry, base current Ib is going to flow, then we are taking the output over here. Now we have unbalanced output like this. Okay, so we are considering output voltage V0 over here. This is my collector resistance RC, and here we will have voltage VEE. Okay, now if you look at this particular circuit, you will find out that we are available with two DC supply. The first one is plus VCC, second one is minus VEE. Okay, and we are going to perform AC analysis of the amplifier. So what we need to do now, we need to replace this DC supply by 0. Okay, so what we will do, we will replace this DC supply. Whenever DC supplies are there, this DC supplies will be replaced by a ground. Okay, so this terminal will be converted to ground, and there is one more terminal over here which needs to be converted to ground. AC signal will remain as it is. While performing DC analysis, we need to zero the AC voltages. While performing AC analysis, we need to zero the DC supplies like this. Okay, so this is our circuit diagram. Okay, this is AC equivalent circuit of differential operator. Okay, I am taking only a single part. Okay, I am not drawing the both the parts. Here we will have another transistors, then another circuits will be there. Okay, so here please note that DC supply is grounded for AC equivalent. Okay, so what will happen because of this? The RC between the collector and ground will be for AC purposes now only. Okay, so this is the conclusion. Thus, collector resistance RC is between collector and ground for AC purpose. Okay, so this one is our AC equivalent circuit of differential amplifier. Okay, so now we have two AC emitter currents, IE1 and IE2, and these are in equal in magnitude, but it will be 180-degree out of phase. Okay, so what will happen? They will cancel each other. That is what we have seen, right? Whenever we have the differential mode operation of differential amplifier, at that time the two input signals provided to the base of two collectors will be same in magnitude but 180-degree out of phase, and they will create the emitter current IE1 and IE2 to flow through the emitter of the two transistors, right? But they are same in magnitude but 180-degree out of phase. Hence what will happen? They will cancel each other to get the resultant AC current through the emitter, which is equal to 0. Okay, so here is our emitter terminal. This is my base terminal, and this is our collector terminal. Okay, so the current flowing through this emitter will now be equal to 0, right? And this is what we have discussed in the last session, right? So for the AC purposes, this emitter terminal can be grounded, and that is what we have done here. Okay, the AC small signal differential amplifier circuit with grounded emitter terminal is shown over here. Okay. Now you can see we have considered the two transistors, and both transistors are matched characteristics. Okay, so what will happen? The AC equivalent circuit for the second transistor will be identical to the this transistor circuit. Okay, so suppose this is the transistor Q1, then the same circuit needs to be applied for transistor Q2 also. Okay, and it will be identical to these circuits only. Okay, so for simplification purpose, we are considering only one AC equivalent circuit of transistor Q1. Okay, and this circuit can be analyzed by considering only one transistor. Okay, and this particular concept is known as half circuit concept of analysis. It is known as half circuit concept of analysis. So we have this particular circuit. Now we will try to find out the differential gain AD for this particular circuit. And as I have discussed with you that we are going to find out, we are going to analyze this circuit using hybrid parameter. Okay, so we will require one hybrid model for this particular circuit. Okay, so I am rearranging the things which are available in this circuit and replacing the parameters with hybrid parameter whenever it is applicable. Okay, so now we have this supply voltage Vs by 2. Okay, so let us start with the supply voltage first. This is my supply voltage Vs by 2. And this is grounded, right? Now let us go back. After that, we have the source resistance Rs, right? So let us have one source resistance Rs in series with the supply voltage signal, right? And then here comes my base terminal of the transistor. Okay. Now in between base and emitter, what we will have? We will have one parameter which is known as HIE. Okay. So let us have, okay, first I will draw emitter terminal over here, which is already grounded, right? So this is our emitter terminal, and in between this emitter terminal and base terminal, I will have one parameter which is HIE. Okay. And then here we have collector terminal. Okay, so collector terminal, what we are measuring? We are measuring output voltage V0 at the collector terminal. So let us take this terminal to measure the output voltage V0, and there is one more resistance which is grounded and it is connected to the collector terminal. Okay, so we will have this resistance RC. Okay, and we know that the collector current IC will flow through the device, okay, the transistor, and we have seen that whenever this transistor is operated in active region, it will behave like a source of current. Okay, so current will be flowing from collector to emitter region, and that is the reason why we need to show this particular region as a source of current, and a value is given by HFE IB. Okay, so this is the amount of current which is flowing from collector to emitter. Okay, IB is small. Okay, so this is my not the exact but the approximate hybrid model. Okay, you can say this is our approximate hybrid model. Okay, So these parameters HIE and HFE we already have seen in the analysis of transistors in basic electronics subject. Okay. So now we are available with the, you can say, AC equivalent circuit with hybrid parameters or H parameters. Okay. And our target is to find out the differential gain AD. Okay. So let us try to find out. Okay. So whenever we want to find out any parameter, we are available with the Kirchhoff's law. Okay. So we have here two input, you can say. One loop is over here. This is called input loop, and one loop is over here, which is called output loop. Okay. So first we will apply Kirchhoff's voltage law to the input loop, and then let us apply KVL to the output loop, and let us see what equations we are getting. Okay. So applying KVL to the input loop, we will have this equation. See the drop across. Okay, there will be a flow of current IB like this. Okay, so there will be a drop across this resistance RS, IB. It is called IBRS. So minus IBRS minus IBHIE plus Vs by 2 equal to 0. Okay, so this is the equation which we are getting. Right now, let us solve this equation for finding out the value of base current IB. Okay, so we will have IB common out of the first two terms. Okay, that is RS plus HIE, and it is equal to minus Vs by 2. Okay, so we will get the value of IB is equal to Vs by 2 times RS plus HIE. Okay, so this is our outcome of first input loop. Okay, we have applied KVL to find out the unknown value of current. Similarly, let us apply KVL to the output loop, and let us see what we are getting. Okay, so now applying KVL to the output loop. Okay, so let us go back to output loop. You can see there is one resistance, there is one source, current source HFE times IB, and there will be a drop across resistance RC. Okay, so ultimately we are available with only one element, and we are measuring output voltage V0. Okay, so this V0 is nothing but the voltage across this RC, and it is equal to HFE IB times RC. Okay, of course in negative because current is going in this particular direction. So we will get the output voltage V0 equal to minus HFE IB times RC. Okay, let us call this as equation number 3. Okay, so we have this equation number 3 where we have the value of IB. Okay, so as per equation number 2, we have the value of IB is equal to Vs by 2 times RS plus RB. Okay, so let us put equation number 2 into equation number 3. Hence, we will get V0 is equal to minus HFE RC Vs upon 2 times RS plus HIE. Okay. Now V0 is my output voltage and Vs is our input voltage, and the ratio of output by input will give us the value of the gain. Okay, so let us take Vs from the right hand side of the equation to the left hand side of the equation. So we will have this ratio V0 by Vs equal to minus HFERC upon 2 times RS plus HIE. Okay, so keep this form and let us give it a number 4. Okay, so here you can see this equation indicates negative sign. Okay, why it is negative sign? Why? Because it indicates the phase difference between the input and output. As I have told you, input and output will be out of phase with each other, and that is the reason why this negative sign is there. Okay, now we know the input signal magnitudes. What is input signal magnitudes? It is Vs by 2. Okay, so magnitude is same, it is equal to Vs by 2, but they are opposite in polarity as they are 180-degree out of phase. Okay, so if we talk about the differential voltage Vd, right, differential voltage Vd, which is nothing but the difference between two input signals V1 minus V2, that is equal to Vs by 2 minus Vs by 2, which is equal to Vs. Okay, so the magnitude of differential gain will now be equal to the magnitude of the differential gain AD is equal to V0 by Vs, and that is equal to HFERC upon 2 times RS plus HIE. Okay, so this is the output. Okay, but this output is for unbalanced output. Okay, this equation is for unbalanced output. Remember, we have measured the output voltage here with respect to ground only. Okay, we are measuring the output voltage with respect to ground only, and that is the reason why whatever gain we are getting, this gain is for unbalanced output. Okay, and here this Vs indicates the differential input. Okay, so the differential gain obtained in this equation, let us call this equation as equation number 5. Okay, this is also one of the important equation. So the gain obtained in this equation is for the circuit where the output is measured with respect to ground. Okay, and that is the reason why it is unbalanced output. Okay, now we are interested to obtain the differential gain for the differential amplifier with balanced output. Okay, and balanced output is across the two collectors of the transistor Q1 and transistor Q2, which are perfectly matched. That means their characteristics are same. So such balanced output will nothing but the double than that which we have obtained above. Okay, so with the unbalanced output we are getting this differential gain, and with the balanced output we will get the same gain 2 times the gain AD. Okay, so for balanced output, gain AD is equal to 2 times HFERC upon 2 times RS plus HIE. Okay, so this 2 will get cancelled out, and we will be available with HFERC upon RS plus HIE. Okay, so this will be the value of differential gain for balanced output differential amplifier. Okay. So now we are available with differential gain in case of differential amplifier for both the cases, for unbalanced output and for balanced output. Okay. This is not the true where we are talking about the DC analysis. In DC analysis, for each and every configurations, we will get the same value of operating points, but these parameters will be different. Okay. So this was about the differential gain of the amplifier. Now let us talk about the common mode gain. Okay. So we have our second point here, which is find out the common mode gain, which is termed as AC. Okay. Now let the magnitude of both AC input signal be Vs and they are in phase with each other. That is what we have seen in common mode of operation. The both the inputs are same in the magnitude as well as in the phase. So what will happen to differential input voltage Vd? Differential input voltage Vd will be equal to 0. Okay. While the common mode input voltage Vc will be the average of two. Okay, and Vc will be the average of two, that is V1 plus V2 by 2. Let us say V1 is equal to Vs and V2 is equal to Vs. So Vs plus Vs by 2 will be equal to Vs. Okay. Now we know how we are expressing the output. Okay. The output is expressed in terms of V0 input Vs and common mode gain AC. Okay. So AC here is nothing but the ratio of output voltage to the differential input voltage. Okay. So this is our case. But now we are operating the differential amplifier in common mode operation. So what will happen? There will be the value of emitter current. Okay, in previous case emitter current was not there, but now you need to consider the value of emitter current. Okay, so we have this constraint over here, but we have emitter current IE1 which is equal to emitter current of transistor 2, and let us take it is equal to IE. Okay, and this amount of current is flowing through resistance RE in the same direction. Okay, so the IE flows through emitter resistance RE in same direction. Okay, so now if I talk about the total current flowing through RE, okay, see IE1 is flowing through transistor 1, IE2 is flowing through transistor 2. Okay, so if we look at the circuit diagram, see this is the emitter terminals of both the transistor and this is my load resistance RE, right? So what happens? Some part of current IE1 is flowing in this direction, some part of current IE2 is flowing in this direction, and there will be the total current which is equal to 2 times IE which is flowing through resistance RE. Okay, so this is the total current flowing through RE. Okay, total current flowing through RE is equal to 2 times the emitter current IE, because we have considered IE1 and IE2 are same, because we are available with the perfectly matched transistors. So same emitter current will flow through it. Okay, so this is what happens. Okay, and this is the equivalent circuit, right? I hope you can let me draw the entire circuit so that we will get the clear cut idea, right? So we have this collector resistance RC This is the collector terminal. This one is the emitter terminal. This is my base terminal where we have provided the input signal Vs. Okay. This is Vs. This is source resistance Rs. This is my DC supply is grounded. This is collector resistance Rc, and this is the first part. Okay, this is emitter resistance Re over here, right? So current IE is flowing in this particular direction. Okay, and same circuit is available over here. Okay, the mirror image of the circuit is available over here, and that is also causing some current IE to flow through it. Okay, so what will happen? There will be a drop across Re because of the current flowing through the circuit. Okay, so this is our AC equivalent. AC equivalent for common mode operation. For common mode operation. Okay, and from this AC equivalent circuit we will be able to find out or make the hybrid model. Okay, so let us now try to derive the hybrid model. Okay, so we have the supply voltage Vs over here, which is grounded. Then there will be source resistance Rs. Okay, then it is connected to base of the transistor. Okay, and in between base and emitter, again we will have gain HIE, input gain. Okay, so here my emitter terminal will be there. Now this time we need to consider this emitter resistance Re. Okay, so in between collector and emitter we will have the output gain or output impedance HOE now. So this is our collector terminal, and definitely one current source will be there. The value of current source is HFE IB. HFE IB. Okay, and we are measuring the output voltage V0 across the collector resistance RC. Okay, so there will be a flow of current. Let us say this current be IL in this particular fashion. Okay, so now we have this current. Okay, load current IL is flowing in this particular direction. Okay, and there is a current HFE IB which is also flowing, right? So we have this current IL coming over here and this current IB coming over here. So ultimately we have total current of IL plus IB which is flowing through this resistance Re. Okay, so this is our approximate hybrid model. Okay, so right now you just consider this particular model. Once you have gone through the network parameters in electrical circuit analysis subject, you will thoroughly understand how this hybrid model is achieved. Okay, so we have this approximate hybrid model. Now as the current through Re is 2 times I, for simplicity of derivation the current can be assumed to be IE and effective emitter resistance be 2Re. That is what I have shown over here. Hence now the emitter resistance is 2 times Re as shown in the figure. Okay, so you can say that the current through resistance RC is equal to load current IL. Okay, current through resistance RC is equal to load current IL. Okay, and what is effective emitter resistance? It is 2 times RE. Effective emitter resistance is 2 times RE. And what is the amount of current flowing through this resistance? It is IL plus IB. So current through emitter resistance is equal to IL plus IB, and current through HOE is the difference between this IL and HFE IB. Okay. So current through HOE is nothing but the difference between the load current and HFE IB. Okay, so these are the parameters which we can derive from this hybrid model. Okay, now apply KVL to the input loop and let us see what we are getting. Okay. So applying Kirchhoff's voltage law to the input loop, we will have this equation minus IBRS minus IBHIE minus 2RE IL plus IB plus supply voltage Vs equal to 0. Okay, so Vs will be equal to IB. Let us take IB common out of the first 3 terms. So we will have RS plus HIE plus 2 times RE plus IL 2 times RE. Okay, so this is our first equation. Okay, let us say equation number 1. Now we know the output voltage V0. What is V0? V0 is nothing but the voltage drop across this RC. Okay, so minus IL times RC. Okay, so V0 will be equal to minus IL times RC. Okay, this is our second equation. Again, this negative sign is due to the assumed direction of the current. Okay, so if we apply KVL to the output loop, okay, if we apply KVL to the output loop, we will get minus IL minus HFEIB divided by HOE minus 2 times RE IL plus IB minus IL RC equal to 0. Okay, so just simplify this thing. We will get IL upon HOE plus HFE upon HOE IB minus 2 REIL minus 2 REIB minus ILRC equal to 0. Okay, so let us take IB common. So IB into HFE by HOE minus 2RE, and let us take IL common. IL into 1 upon HOE plus 2RE plus RC. Okay. So now you can further reduce this equation to HFE minus 2RE HOE, it is equal to IL 1 plus HOE 2RE plus RC. Okay, so we will get the ratio of this IL and IB in this case, and that is equal to HFE minus 2RE HOE upon 1 plus HOE 2RE plus RC. Okay, so this is our equation. Let us talk this equation number 3. Okay, and we have this equation number 1. So now from this equation number 3 we will get the value of IB. Okay, so if we put the value of IB, that means put 3 into 1, we will get, okay, now I will directly write down the equation which we are getting. Vs by IL is equal to 1 plus HOE 2 times RE plus RC into RS plus HIE plus 2RE divided by HFE minus 2RE HOE plus 2 times RE. Okay, so this is what we are getting. Now if you are able to find out the LCM and if you simplify the equations, then we will be able to get the equations like this. Okay, so I am directly writing down the equation. Okay, so simplification of this equation is up to you. Okay, you have to derive this equation. 2RE into 1 plus HFE plus RS plus HIE into 1 plus 2 times RE HOE divided by HFE minus 2RE HOE. Okay, so from these equations take the LCM and simplify the terms, you will be able to get this equation. Okay, let us call this equation as equation number 4. Okay, now we have the value of IL now. Okay, so if we put this value of IL in this equation, equation number 2, then we will be able to get the V0 and Vs. Okay, and V0 and ratio of V0 by Vs is nothing but the gain of the circuit. Okay, so put IL into equation number 2. Okay, so we will get V0 is equal to minus Vs HFE minus 2RE HOE into RC upon 2 times RE into 1 plus HFE plus RS plus HIE into 1 plus 2 times RE HOE. Okay, so now we have this V0 and on the right hand side of the equation we have Vs. Just bring that Vs at the right hand side so that we will get the AC, which is nothing but the ratio of V0 by Vs, and it is equal to 2RE HOE minus HFE into RC upon 2RE into 1 plus HFE plus RS plus HIE into 1 plus 2RE HOE. Okay. Now, in the second semester, you have seen that whenever we talk about the HOE, in practice, this HOE is the parameter which is generally neglected. Okay. So, if we neglect this parameter, then you can further reduce the value of common mode gain, and it is equal to minus HFE-RC upon RS plus HIE plus 2 times RE into 1 plus HFE. Okay. So this is the desired equation. Okay. This equation pertains to the common mode gain of the differential amplifier. Okay. And this common mode gain equation remains same whether our output is balanced or imbalanced. So irrespective of the configurations we are using, we will be able to get the same equation. Okay, it is not same in case of differential gain where we are getting two different equations of differential gain AD, but the common mode gain will be same for each and every configurations of the differential amplifier. Okay, so this is what we have got. Okay, now we shall stop here. In the next lecture, we will continue with this and we will try to find out the common mode rejection ratio as well as input impedance and output impedance of the differential amplifier. Okay, so all the parameters which are required for the performance of the differential amplifiers will be completed. Okay, so we are performing two different analyses for finding out the different parameters. For finding out the operating point, we will do the DC analysis, and for finding out the performance parameter, that is gains and input and output resistances, we will perform AC analysis. Okay, so we will stop here. If you have any questions, then you are free to ask.